All right, hello everybody. Welcome to today's walkthrough. And if you're here for a problem set walkthrough, you're in the wrong spot. This is a test review. Obviously, we've reached the midpoint of the course. The test is this Friday. And in today's review, we're going to kind of quickly go through all the topics that we've talked about in CS50 at a pretty high level. Obviously, we've had 6 lectures, so we can't really dive too deep into every topic that we have discussed. But we do want to give you a sense or refresh your memory on what some of these topics were, because these are topics that are fair game for the test. So information about the test is available at this link here, which is also on the front page of the course website. But here are some of the bullet point takeaways. You will have a 72-hour window to work on the test, but it is not expected to take you 72 hours to do it. It's designed to take a couple of hours. So hopefully if you get started early on Friday, you can go through a couple of problems, take a break, pick up the next day or something like that. But again, it's not designed to take you 3 full days to do it, so try not to allow that to happen. It's going to be released Friday at noon, just like a problem set specification would be. There'll probably be some distribution code or something like that that you will download into your CS50 IDE. And you'll also be submitting the test via CS50 IDE as well, using the Submit 50 tool, no later than Monday, the 17th at noon. Just to anticipate a common FAQ at the last minute, do make sure that you run Update 50 before you attempt to submit the test. We push new changes to Update 50 that allow you to submit new problems, and the test will be one of those problems. So if you don't run Update 50, you may end up in a situation where it will tell you that it failed to submit, and it might be because you left your IDE out of date. So some of the resources to consider as you're studying for the test. The syllabus has a list of all the topics that we've covered, and again, we're going to go through pretty much all of those at a very high level in today's review session. But as the test prep guide recommends, we do encourage you to take a look at lecture notes to review the sample source code that David presents in lecture, those lecture examples, his slides, and watch or rewatch the lecture videos in that order in terms of prioritizing your study. So you don't necessarily have to start by diving into the video, which would take an hour and a half to watch or to rewatch. You might want to start by looking at the notes and being able to then home in on those parts of the video that you feel that you could use a refresher on. And also take a look at problem set specifications, any distribution code that we released for PSETs 3, 4, and 5. The postmortems, all the postmortems for problem sets 1 through 5 are on the course's website under problem sets. So you can see with Rob walking through the staff solution. So if you struggle with a particular aspect of an assignment, you can see how the staff might have tackled that, and hopefully that will get some gears turning about how you could have approached it, and hopefully that will help you as you begin to study for the test. Some additional resources, office hours. There'll be office hours today. There have been office hours all this week, but there are office hours in HSA today until 5 o'clock, and tonight in Widener as usual from 9 to 11. Tomorrow in HSA as well from 10 to just after 5 o'clock. And tomorrow night's office hours, Thursday night's office hours are actually in the Quad. They are not in Widener this Thursday. They are in the Quad. I'm not going to say that because I know there's controversy of the way that gets pronounced. But that building right there, 9 to 11 p.m., but they will be in the Quad, not in Widener tomorrow. There are no office hours during the test. So no HSA office hours, no large office hours, anything like that during the test period. And there are also no office hours next week during the coding contest, which is the activity that we have next week instead of problem set 6, which will be released 2 weeks out, or a week and a half out. There's also CS50 Discuss. If you haven't used this tool, it's a really good one to take advantage of. You can search through questions by just typing in a search box and looking for a particular phrase that maybe your classmates have asked about or you have asked about to get a refresher on that answer. You can post questions there, and the staff is actively monitoring it up through Thursday evening, but we will not be responding to any questions on Discuss during the test period, but we will be checking in on Discuss. And do remember that the only humans that you can turn to for help during the test are the course's heads. You can't talk to your teaching fellow about it. You can't talk to classmates about it when you're working on the test. It is a take-home, but you are expected to work on it by yourself. And if you have any questions about it, to only turn to the course's heads. And if you have any questions, please just let us know. Lastly, there is a quiz bank So over the last 9 years, we've asked a variety of different types of questions. We've had quizzes every year we've done CS50. They are available at this link, which you may not have ever seen before, quizbank.cs50.net. There's no login required. It says there's a login at the top, but that's an administrative thing. You don't have to actually log in to access any of this information. It is an archive of every question that we've ever asked in a quiz before, and we sort of semantically categorize them by what topic they tend to focus on or hit on in the question. So if you're looking for questions on binary search, or you're looking for questions on stacks and queues or something like that, you can actually go in there and choose from a drop-down and check those boxes and get a search generated of those questions, along with answers and explanations as well. So feel free to use those to help you study for the test. Know that we are changing the format of the test this year, obviously. In the past they have been timed 75-minute exercises in class. Now they are not, so the question format will not be quite the same, but the content of the questions, the types of things we're asking about will be the same. Are there any questions administratively about anything about the quiz before we begin?
Those resources will be available during the whole...
All of those resources will be available. So any electronic resource that we have offered will continue to be offered. The only difference is CS50 Discuss will not be monitored by staff. We won't be responding to any questions, any new questions that come up during. But the quiz bank will be available, CS50 Discuss will be available. All of that remains open to you, as well as any other resource outside of CS50 that is electronic and non-human that you want to take advantage of. Other questions? I saw a couple other hands, yeah.
Where does that other electronic resources
Well, if you want to like Google something or anything like that would be totally fine. But like talking to a tutor or talking to a TF or something like that would not.
We've tried to construct things such that you shouldn't be able to just Google a problem, but if you do happen to Google a problem and see the solution, then don't cross the line and just copy that. But for the most part, like if you don't understand some aspect of a problem, you're free to Google.
Okay. Other questions? Is there any like right in the middle there? I can't see your hand because I'm getting blinded. Okay, well if there are any other, is there one back there? Can you speak a little louder? There's liable to be a mix of both. The question was, are there going to be coding questions or fact-based? And there's liable to be a mix of both. Just like in quizzes in the past, we've had small coding exercises and sort of regurgitation type things where you're trying to pull facts out of memory. The difference this time being that you are not timed, so you can look these things up, which should help. So liable to be a mix of both, questions that do coding and questions that do not. And of course, for coding questions, you're welcome to use CS50 IDE to implement and debug and test and run your code, which is something that we were not able to do in the past because the quizzes were based on paper.
Yeah, so if you look at past exams, the short answer questions and coding problems are very potential candidates for the exam, whereas the true and false and multiple choice are probably less likely just because the nature of the exam is different, and true and false question would be very easily Googleable.
Yeah.
Yes? You'll be instructed to put answers in specific files inside of a directory in your IDE, and then just like at the end of a problem set, you zip up those files and upload with Submit 50. It'll be exactly the same process. Yes? No, it's heads@cs50 is the only email address that you can email for help during the test, but not teaching fellows. There's no what? There's no in-person help offered during the test.
Right, the help that's offered, that's mostly supposed to be for if there is something that's too vague with a question that you might have a question about, that, like making the question more specific, or if you think there might be an error in a question, those sorts of things. But if you just have a general question about it, like you don't understand how to go about it, those are the sorts of things we're not going to answer.
Yeah, logistical questions, administrative type.
Yeah. Just like how in an in-person test, you wouldn't like ask the proctor to like come and like start clarifying things, so just clarification questions.
Any others before we start to dive into topics? If there are any others, just feel free to come seek any one of us out at the end today too, and we'll be happy to to answer those. All right, so let's start to move through. So we've had 6 lectures. Again, week 6's lecture was released last week, but is not on the test. So nothing about HTTP or any of that stuff, if you've watched that lecture already, is on the test. And let's start with week 0, and the very first topic that we talked about, which was binary. So remember that binary is a counting system. It's a counting system in particular used by computers, whereas we humans have decimal system, and we have 10 digits we can use, 0 through 9, and multiply those place values. We have the ones place, tens, 100s. A computer uses 2 digits, or bits, 0 and 1, off or on. But otherwise, the counting system really does kind of remain the same. The place values are not powers of 10 anymore. They're powers of 2. And on top of that binary, we can layer on something called ASCII. The ASCII standard, remember, is a system that was devised about 50 years ago or so to standardize how we or rather how a computer represents a collection of 8 bits, 8 zeros and ones, which translate to some decimal number, as a letter. So that if I am using a computer in the United States and I'm typing the character A, underneath the hood, the system is recognizing that as a 65. And similarly, if I was on a computer in France or anywhere else really, that might have a different keyboard layout or anything else like that, that those values are represented the same. It'll be a 65 regardless of where you are. The system is kind of arbitrary, although it does have some patterns to it. So all the alphabet characters proceed in order. So capital A is 65, and capital B is 66, and so on and so on. Why it's 65 and 66, I couldn't really tell you. It's just sort of an arbitrary but somewhat meaningful standard. Lowercase a is 97. These 2 little tidbits of information might be just good to have at the front of your mind. Again, you can always look up the ASCII table during the test, but it can save you a few steps if you just remember those 2 little pieces of information possibly, because if there's any questions about, like similar to what you saw in problem set 2, that could be pretty helpful. And then we talked about bytes. We talked about why is a 65 in my calculator system different from a 65 in Microsoft Word, where that might be represented as a capital A, which is different from if I'm in Photoshop, maybe that 65 represents the amount of red that is in a pixel, right? And so we learned that whatever file you're in, or the file extension you're in, or something like that, matters in terms of how that byte, which again, everything on our machine ultimately boils down to zeros and ones. It's how those zeros and ones are interpreted in our programs that make a difference. Lastly, at the end of week 0, we talked about algorithms. Algorithms are step-by-step sets of instructions that we use to solve a problem or to complete a task. And we talked about a couple of different types of algorithms. We talked about how to count the class, where everybody stood up and gave themselves the number 1, found a partner to pair off with. They both added their numbers together. That was their new number, so then everybody in the class was still standing up, thinking of the number 2. And then exactly 1 person from that pair sat down. So half of the class sat down, but everybody that was remaining standing was the number 2. And we could keep repeating this process over and over until there was just 1 person left. And that would ultimately, hopefully, although rarely, result in the number of people that are in the class. And the reason I say rarely is not because this algorithm is incorrect. It actually works, but rather because we as humans, when we are, there's the social awkwardness of yelling across the room or something like that, we sort of create these bugs in our algorithms that should otherwise be correct. And we talked about binary search, the most efficient way to find somebody in a phone book. It's not necessarily starting at the beginning and going 1 page at a time, but maybe because we can rely on the fact that a phone book is alphabetically sorted, we can sort of open to the middle of the phone book, tear that problem in half, and we've eliminated 1/2 of the problem, which in a 1,000-page phone book, we've eliminated 500 pieces of data that are not going to be what we're looking for. So we have this question of correctness versus efficiency that we talked about. Both of those algorithms, the binary search algorithm where we're tearing that phone book in half, and the algorithm where we're going 1 page at a time, they're both correct. They both work. They both do what we say they're going to do. But there's a very different level of efficiency. The binary search, the tearing it in half, is going to go much faster in terms of how its steps play out than the linear search algorithm will. And so when we're talking about algorithms, it's important to keep in mind this distinction between a correct algorithm and an efficient algorithm. And then at the very, very end of of week 0, we introduced Scratch. And we talked about it again a little bit more in week 1. But Scratch has these different types of blocks. And in week 1, we eventually transitioned to talking about this in C and translating these blocks from Scratch to C. But we have these ideas of control blocks. So things like loops or conditions. We have data, variables, sounds. Our programs could play different things. We could create our own custom blocks. Remember, we had the example of cough, which made use of the say block to allow us to cough or say something multiple times. And then we have events, when green flag clicked, when touching edge. These are things that will only occur. They're sort of a form of condition, but they depend on something sort of external to our program or while our program is happening, occurring. So that's high-level gloss of week 0. Questions about any of these general areas that we want to address now?
So it could be if you want us to explain something more, or if you want to see an example of something, or pretty much any question you might have about this material. We should talk about it now. Any of it could appear on the exam.
Yes? I mean, we could ask you to take a look at a Scratch program and write something about, you know, what the events are, like detail the events and when they trigger and what they do. We could ask you to create a Scratch program and take a screenshot of it and upload that as a PNG or something like that into your IDE. So there's different options. We certainly could test on it in either of those ways or others. Yes? Is it arbitrary that a byte is 8 bits? Yeah, probably.
For the most part. The nice thing about 8 is like it's a power of 2, and they just standardize on let's make 8 bits be like the fundamental unit. If they had decided 16 bits, then it would have been 16 bits, but 8 bits is like a nice small number, but also big enough to sort of, like working with 1 bit, why don't we just work in bits? Because that's too small. What about 2 bits? Well, that's still pretty small. 4 bits, now we're getting a little bit bigger, but it's still kind of small. 8 bits happens to be like big enough to be worthwhile number of bits to work with at a given time.
When we talk about the size of different data types and stuff? Yes, they're always in bytes. Correct. And we'll talk a little bit, very shortly actually, about the different sizes that different data types take up. But actually the size of a byte is one of those also arbitrary things. The ASCII standard, if you actually take a look at it, is actually defined as 7-bit bytes. So that was also one of those things that was not immediately agreed upon and then was subsequently agreed upon after, you know, conferences and people voting on stuff and papers, that we would standardize on this concept of an 8-bit byte. All right. So after week 0, we immediately sort of jettisoned Scratch in favor of C, a text-based programming language that has much of the same functionality of Scratch, but also allows us to be so much more expressive and do so much more complex problem solving within it. And the first thing we talked about was loops. And I do see a couple people out of the corner of my eye like taking pictures of these slides. We will make these slides available to you, so you can take notes if you want, but these slides will be available after today's walkthrough as well. So C provides these 3 different kinds of loops, and why does it do different kinds of loops? Like a loop is going to do something multiple times. Really for not every case, but in a lot of cases, all 3 of these loops, I would say, are interchangeable. If you can write a program using a for loop, you can pretty much translate it into a program that uses a while loop by modifying the syntax a little bit. So when I put these notes up here, like a for loop is used for running a specific number of times, or a while loop runs an unknown number of times, possibly 0, and a do while loop runs an unknown number of times, but at least once, that's not to say that's the only circumstance in which we're allowed to use that kind of loop, but that's the sort of the common circumstance. If I know I want to do something 100 times, I'm usually going to use a for loop that iterates from I is equal to 0 up to I is less than 100, just because I happen to know that number ahead of time. But again, all of these are sort of interchangeable. While loops will do something possibly infinitely, so we might use those in the context of a game, like we did in problem set 3, where we had a while loop that was just constantly running until it was broken out of by that, the one function being triggered. So if the game was successfully won, that was the only situation in which we would break out of the loop. And a do-while loop we use for things like prompting, where we know we're going to have to ask the user to give us a value at least one time, the size of Mario's pyramid or how much change they want. And depending on how difficult the user is being, if they give us a negative number or they type in a word or something like that, we might have to keep prompting them over and over and over until we get a value that we want. That's a good use case for a do-while loop, is prompting a user. In addition to loops, we have conditions. And the first thing we talk about in conditions is a Boolean expression. It's sort of a complicated phrase, but it really boils down to a yes or no question, true or false. And we have, ands and ors and nots and all these things, but ultimately a Boolean expression just boils down to true or false. It asks a question, are these two things equal, or is one less than the other? Is this true and this true? Those Boolean expressions go into things like if blocks or if statements, where we ask a question, if something is true, then we'll execute this code. Else, if this thing is true, so if the first thing is not true but the second one is true, then we'll do this. Else, so if neither of those first two things is true, then we'll execute the code that's between our third set of curly braces. So a conditional basically allows us to make a decision. We get to a fork in the road and we decide which path we're going to take. The difference between an if and a switch is that we use switches when variables can only take on discrete values. So we have case statements. We might have a switch on a variable x. Case 1, we do this. Case 2, we do this. Default, anything other than case 1 or case 2, we do some other thing. So we can't use ranges. We can't say if x is less than 5 in the context of a switch. So switches are used for discrete values. And then you may have occasionally seen this thing called the ternary operator, ? It's really just a shorthand way of doing an if-else statement. There's a couple of examples of this in problem set 5. If you look at the distribution code for Speller, we use a ternary operator to decide whether we're going to use the default large dictionary, or if you supplied 3 command line arguments in that program, we'll use the dictionary that you told us to use. So that's an example of using a ? Or a ternary operator in context. Again, this is really more about knowing what this is than necessarily having to use it on the test. We certainly aren't expecting you to use ? if you haven't seen it before, but it is good to know possibly what that is in case you encounter it. So after loops and conditions, we had variables. We have these things, they're basically just containers, and they're containers that have a name. And we can put a piece of information into the container. Maybe it's literally just a bowl, and I take the number 5 and I put it in the bowl, and this bowl is called x. Maybe I want to increment x. I'm going to keep this same bowl. I'm not going to create a new bowl with 6 in it. Maybe I just want to take that 5 out of the bowl and put 6 in. So variables are basically just containers that allow us to, a term that some people might use is mutable, where we can change what we find there as opposed to a constant, right? We can't say 5 equals 6. That doesn't make any sense, but we can say x equals 5, and then we can say x equals 6. By saying x equals 5, we're not saying x and 5 are permanently intertwined. We're just saying for now, what we find in this bucket or this bowl called x is the number 5, and we can change it if we want to. Assignment, remember, works right to left in C. So the value on the right of an equal sign gets put into whatever is on the left. So x equals 5 means we take 5 and we put it into x. 5 equals x would not be valid. You get a compiler error if you tried to do something like that, because basically what you're saying is you're trying to overwrite the value of some constant 5 with some other piece of information. Remember in C that every variable also has to have a type specifier. We have to say exactly what kind of data can go into a particular bowl, and we can never put something of another data type, or that's an overphrase. We shouldn't put stuff of another data type into a variable, and there are a couple cases where you can get away with that, but generally best practice to avoid doing something like that. When we get to Python after the test and after the coding contest, you'll see that modern languages, many of them, including Python, do not require you to do something like this. You don't have to say, this is a container called x into which I can put integers. You just say this is a container called x, and I am going to be able to put whatever I want into x. Then we talked about compiling. So when we write our C programs, that's not the final step of the story. We don't write hello.c and then immediately execute it. There's this step that goes in between where we have to translate this C code that we understand, that humans understand, but machines don't. Machines only understand zeros and ones, and so we have to compile it. We have to translate our code from a human understandable language like C into something a machine understands. But make, which is how we usually do this, is not itself a compiler. This is sort of a trick question that has come up in the past. Make is not itself a compiler. It is a utility that we use that allows us to tell a compiler. We can add additional flags or parameters, and so sometimes if you run make, particularly if you have updated your IDE recently, you might notice that the command that is then executed is quite a bit longer now. We have clang, I think it's like -f, sanitize, -integer. We have all these flags that we've added that you don't need to understand what all of those flags do, but basically make is preparing a set of instructions for clang. Clang is the actual compiler that it needs to take our source code and translate it into machine code. Computers do only understand this machine code, though, these zeros and ones, and the compiling process is actually multi-layered. There are 4 different parts of the process of what we call compiling, and they are pre-processing, where we take things like #define, where we can assign a symbolic value to a constant. So in pre-processing, all of those will get replaced with, so all of our alphabet size, if we used alphabet size as 26, #define that. During pre-processing, all of our uses of alphabet size would get replaced with 26. And similarly, would all of our #includes actually go and get the contents of standardIO.h or CS50.h and paste that effectively on top of our files. Compiling, which is one subset of compiling, is the part of the process where we take our source code and translate it into assembly code, which is sort of, it's an intermediate step along the way. It's much smaller instructions to the computer. During assembling, those very small instructions are actually turned into zeros and ones that the computer understands. And in linking, we take our zeros and ones that we wrote, that the computer has assembled at this point, and we tie those in or mix those in with any other zeros and ones of other libraries or sources that we rely upon. So at this point, it's during the linking portion of compiling that the zeros and ones of CS50.c, where we actually define functions like getString and getFloat, that's where those actually get mashed into your program as well, so that your program can actually make use of those. It actually goes and gets the zeros and ones of that file and ties it in, so it doesn't have to rely on an internet connection or something like that to be able to see how those functions work. Okay. Data types. To get at the question that was hinted at earlier, we have different data types in C. There's different native ones: integer, character, float, double, long. There are others. We have some additional ones that we've provided for you: bool and string. And then there's this notion of signed and unsigned. Does anybody remember what the difference is between signed and unsigned? Signed can be negative or positive, and unsigned can be positive only. So it basically allows us to shift the range of numbers that we represent from, in the case of an integer, -2 to the 31st power up to +2 to the 31st power, basically. We can shift it instead from 0 to 2 to the 32nd power. So we get to double how high we can go at the expense of no longer being able to rely on negative numbers. And these are the different amounts of space that these things take up. So a bool or a character takes up 1 byte. And really, we could represent a bool as a bit, right? It's just true or false, on or off. But unfortunately, the way we've implemented it, we're stuck with having to use a full byte worth of space, so slightly inefficient. We could be 8 times better. Floats and integers take up 4 bytes worth of space. Doubles, longs, and strings take up 8 bytes of space, but that's sort of an abstraction that we later peeled away in the course, where a string is really just a pointer to a character, so we're jumping a little bit ahead here. And pointers on our system take up 8 bytes, and that's why a string will always show up as being 8 bytes, even though clearly we can write strings that are much longer than 8 bytes, because when we're talking about a string, we really are just talking about a pointer to the first character of this array of characters that is eventually terminated by a \0. 2 more concepts that we touched on in week 1 was overflow. So overflow is what happens when you try and store a value that is too large for the container that you have allocated. So if we have integers, we can go, as I said, from 0. If we have an unsigned integer, we can go from 0 to 2 to the 32nd power. If we try and store anything bigger than that, we can't. We don't have 33 or 34 or 35 bits to work with. And so the highest bits just kind of get discarded and thrown away, and we end up wrapping around or overflowing back to the lowest possible value and going back up again from there. So that's the basic idea behind overflow. And imprecision, which is the counterpart for floating point numbers, is really quite similar. It's that there are an infinite number of floating point values that we could represent, going out to however many decimal places we want, but we can't possibly represent every single one. And so the best we can hope for is to get close enough that it won't matter that we're a little bit off. We can only store so many pieces of information in those 4 bytes. And we saw in lecture a case where it did matter, right? Remember the Patriot missile video where we didn't have enough room to hold all the data that we needed, and that ended up being a catastrophic failure. So these problems of overflow and imprecision, in a vacuum in CS50, they're kind of annoying, but in the real world they can have real consequences, and that's sort of the underlying reason for it, is just having a limited amount of space in which to store information. Week 1, questions. Those are all the high order bits here. No? Okay. Yes? What was the ternary operator? It's question mark colon. Now that my keyboard isn't working for some reason. It's question mark colon, and it basically allows us a shorthand way of doing if else. So it's a very short conditional. I could say something like if, and then I put a Boolean expression, question mark. If the Boolean expression is true, it will, I can switch it to the surface. If the expression is true,
Something arbitrary.
I think it's actually this.
The parens don't actually matter at all.
Oh, really?
I didn't need to put any parentheses, so.
So basically what this is happening is it's asking the question, is 3 greater than 4? If so, x's value is 7. If not, x's value is 10.
So this will happen to evaluate to 10 because 3 is not greater than 4. But you could make this condition be whatever you wanted.
And a note that when the right side is evaluated, it's going to get assigned to x.
Yes, so everything on the right side, just like with any assignment, everything on the right side is going to happen first until it boils down to some entity that we can assign, and only then will that value get assigned to the thing on the right.
Yeah.
And now I learned that parentheses don't matter in the context of ternary operator.
Nice.
All right. So week 2, we started to introduce, what?
There we go.
There we go. We started to introduce bugs. So our code before then, of course, was perfect. We never made a mistake at all. But in week 2, we started to introduce bugs and how to solve these kinds of issues that crop up in our code. And we learned about things like implicit declaration of functions, which happens when we fail to include a header file maybe that has printf in it. If we just use printf without having pound included standard IO, we'll have an implicit declaration of printf. We won't know where printf came from. Or if we define a function ourselves but fail to declare it, that could happen as well. We have things like use of undeclared identifier, where we use a variable without having defined it. We just say, instead of this, if we had failed to define x previously, if we hadn't declared x before, this would now result in use of undeclared identifier, because x just sort of came out of nowhere. The computer has no idea what you're talking about. And so you'll get this problem. And I only introduced these errors because these are some of the most common ones that we might see at the very beginning of the course, and it's the kind of thing where it might be, again, good to have this at the forefront of your mind instead of having to Google it. But of course, you can Google it, you can search it if you see something like this during the test. Out of bounds errors, which might not actually be bugs that stop our program from being compiled like these other two, but these are logical errors where instead of printing every element of an array, of a 10-element array from 0 to 9, which is what we're supposed to do, if we accidentally iterate from 0 to 10, and because we count from 0, 10 is the 11th element of this 10-element array, we can go out of bounds and we can suffer serious problems, particularly when we start to do this in the context of command line arguments, where we go really far out of bounds. We can suffer things like segmentation faults, which happen when we touch a segment of memory, we do something to a segment of memory that we do not have access to. We didn't allocate it, and something else is using it. It might actually be the code that is literally running your program, something else in the system that is telling your computer which instruction to run next. If you overwrite that, your program is going to crash out, and that's what a segmentation fault can be. Know that there are these tools, Help 50 and Debug 50, and if you haven't used them, you may want to familiarize yourself with them. Help 50 just takes some of these error messages that can be really cryptic, particularly from Clang or Valgrind, and hopes to translate them for you. And Debug 50 allows you to inspect what is happening in your program as your program is happening. And so if there are coding exercises on the test and you are trying to work through them, you're not going to have something like check 50 to test your program, so you might want to use Debug 50 to open up your program while it is running, set a breakpoint in your program, and try and figure out where things might be going wrong so that you ultimately get the output that we're hoping your program will produce. We talked about cryptography. That was the big focus of problem set 2. Cryptography is about obscuring information, and we learned about something called a rotational cipher. Caesar and Vigenère are both rotational ciphers. The Caesar cipher works by shifting every single character of your message by the same amount, so turning all of your A's into B's, or turning all of your A's into C's, and similarly changing all of your other letters by the same amount. Whereas Vigenère does that on a letter-by-letter basis, changing each letter by a different amount tied to some keyword as opposed to just some constant number that we're passing into the program. So knowing what a rotational cipher is, or knowing what cryptography is all about, is sort of the cornerstone to take away from this particular topic. Then we learned about strings, which we immediately introduced as a sequence of characters and then immediately changed to describe as an array of characters. So an array is a collection of data of a similar type. So we can have a set of 10 integers, but we don't have to define each one of them individually with int, A1, int A2, int A3, all of that. That gets old really fast, and so we can instead just declare, I want this array, int A, square brackets 10, and that will give us an array of 10 integers. In particular, in the context of a string, it's an array of characters. It's just an array of letters and punctuation. The length of a string we can always get with the function strlen. And once we know the length of the string, we can access any individual character of that string that we want. So we can say str square bracket I, and I can be any value between 0. It can be equal to or greater than 0, but less than strlen. So if I have a 5-character string, I can access str 0, 1, 2, 3, and 4 safely. If I access 5 or anything greater than 5 or anything less than 0, which is also possible in C, you can have negative indexes. Again, bad things are probably going to happen if you do.
Well, you can access 5 because you know it'll be \0.
Oh, that's
but
true.
But anything past that will be bad.
Because all strings do end with that \0 character. And the reason that strings end with \0 is because of the way the system interprets them, because as I sort of hinted earlier, a string is just a pointer to the first character. At the end of the day, a string is just a pointer to the first character of an array of characters. That \0 tells our system when to stop printing out what it sees. It just sees memory as this sort of unending line of bytes that it has access to. It could just print the entire thing. It could print every byte of memory that it sees until it hits one that's a \0. That's the only way it really knows how to stop. And that's why that is there, so that when we're printing out strings, the system knows when to stop actually printing it out. Then we talked about typecasting, or we briefly talked about typecasting, and we introduced it in the context of ASCII, how to recreate the ASCII table. We can treat, that bottom line gets a little cut off there, but we can treat characters as numbers, and we can do math with them. In fact, that was the whole premise of problem set 2. And the thing you can't see up there, but you can see here, is that explicit typecasting, which we don't always have to do, but we can convert one data type to another explicitly if we want to. So if I want to know the ASCII value of something, so maybe I have something like this, char c is equal to get char, and I have no idea what ASCII value the user printed out, but maybe, or the ASCII value of the character the user typed in, but maybe I want to know. What I can then say is, well, I could print this out, and since I know I'm going to want an integer, I'm going to use %i. I'll just add a \n for clarity. but I want you to take this character that you just got, but I want you to treat it like it's an integer instead of a character. That's an explicit typecast, and what will happen here is it will print out whatever the ASCII value is of the character the user typed. But we don't have to do an explicit typecast. C is smart enough to know that if I just said this and left that out, because I'm asking for an integer here, it will still implicitly cast that to an integer. So that's what we talk about typecasting. It's really just saying, I would like you to temporarily treat this variable as if it's a variable of a different data type. That's what a typecast allows us to do. We introduced reference tools. We talked about manual pages. So if you don't ever know what a function does, you can, within CS50 IDE, you can type man and then the name of the function. And that will give you this basically user's guide of how to write, of how to work with that function. Some of these are a little difficult to read. Some of them are actually pretty complex. And so several years ago, we wrote a tool called Reference50, where you can do this exact same thing. And there are many online equivalents for this for C and for other languages. These will probably, there are many Python online references, PHP, JavaScript, all these things that we will see later in the course. And you know, we've spent now 6 or 7 weeks talking about C, and we're not going to have 6 or 7 weeks to talk about Python or JavaScript or SQL in quite the same amount of depth. And so you might rely on resources like this to further your understanding. And you might rely on resources like this during the test as well, where in office hours you might have asked, you know, what function can I use to do this? Instead, you might want to now consult the reference guide if you haven't already. Become familiar with it so that if you need to look up a function on the test or you see a function that we use that you've never seen before, you know where to look it up to find it. And then we ended week 2 by introducing command line arguments, which we used, of course, quite extensively in problem set 2. But command line arguments allow the user to supply extra information to our program before the program is running. Up until this point, we had to prompt the user, like we did in Mario and Greedy, to give us a value at runtime. But now we can ask the user to supply something before the program has started running, and we can use that information to make perhaps a very early snap decision in our program about what to do. So if the user didn't give me that extra piece of information I asked for, I'm not going to try and work through all the stuff I was going to do. I'm just going to say, well, I'm done. You didn't give me the command line argument that I asked for. We change our declaration of main to, instead of being int main void, which means my program accepts no command line arguments, to int main int argc string argv square brackets. It's a mouthful, but basically what this boils down to is argc is how many things do the user type at the command line, each one separated by a space, and argv is what do they actually type, so you can access those pieces of information if you need them in your program. Questions about week 2's material? Yes? When you use debug 50, how would you suggest where to use the where to put the breakpoint? If you suspect that your code is, if you have a program where there are multiple functions, so you have main and you run another function that calls some other function, go with the narrowest scope first. So go with the most buried in function. That way you're not having to step through quite so much stuff. Would be my recommendation. If you have literally no idea where your program is going wrong, put a breakpoint at the very first line of main and just step through as you go. But if you think you know generally where it is, and this is why when you're writing programs, like writing functions is a good thing, because you can, so far I've only been writing, we'll use problem set 3 as an example. So far you've only been writing init, right, the initialize function. You don't need to put your breakpoint in main. You can put your breakpoint in initialize because you've only been working there and just have it stop once it gets there and then begin to step through. So if you know where the problem is, put it at the very first line of the function or where in the program you think it's happening. But otherwise, if you have absolutely no idea, you set it at the very beginning of main so that you can just step through line by line by line.
It's also the sort of thing you could do a binary search on, that like if you have a 100-line program and you have no idea where the problem is, we'll set a breakpoint at line 50 and do things look right at this line of code. If they do, then try setting up a breakpoint at line 75. If they don't look right, try running again by setting one at line 25. And just sort of figure out, like, you know what the program should look like at various points, or at least what you think the program should look like. And if that matches up with what it actually looks like at that line of code, then you can figure out from there.
Yeah, always make sure you're looking at the values of like your variables that you care about and like think about what you're expecting at each point after each line is executed and before each line is executed. And if that like starts to differ from your expectations, then your problem is like probably happening somewhere around like where you are right now.
And a really quick note for those of you who have not used debug 50 extensively about the difference between step over and step into, which can sometimes be a kind of a sticking point. If you step into a function, you will leave your current function and go into that function. It makes sense, right? Step into. But if you step into something like printf or some other library function, you're going to suddenly find yourself like kind of in the weeds, and it's going to look the code's going to look really, really weird. So if you're about to make a function call to a system function like printf, step over that. Printf works. It's not a problem in printf. But if you're about to make a function call to one of your own functions, that's when you might want to use step over instead of step into. I know it can slow people down sometimes if they accidentally step into something. Although there's also that play button that just will ignore, it will stop stepping through line by line and wait. And if you set your breakpoint in a loop, it will immediately break again once it hits that point again. But yeah, debug 50 is definitely a good thing to practice with if you haven't practiced with it before. It's really very useful.
Mm-hmm. Yeah. You can just like, to access the manual pages for like any function that you want to know what it does, you would just like type in your terminal man and then like the name of the respective function.
Man printf.
Yeah.
All right. So week 3, we talked about 2 big things pretty much exclusively. We talked about searching and we talked about sorting. Searching, we talked about 2 different algorithms for this. Linear search, which you can perform on any array, and it starts at the beginning, and it goes step by step by step by step to try and find some target that you're looking for. Binary search, you cannot use on any array. Your array has to be sorted first. But given that your array is sorted, you get to take advantage of this amazing power that it has to throw away half of whatever is left, because it knows, well, if this array is sorted and I'm at the midpoint and I'm looking for 20, but at the midpoint I find 15, well, I know that it can't possibly be anything over here because everything over here is less than 15. So it's going to have to be over here, and I can discard half at a time. So binary search generally will run much faster than a linear search, especially as n gets larger and larger and larger, but it has that caveat where it has to be sorted first. And we have 4 different ways that we've talked about in the course to sort, and we're not going to go step by step into what all of those algorithms do. There's lots of videos on this topic, but the basic gist of these 4 algorithms, if you're working through them or you want to use one of them, is as follows. Selection sort is you look through the entire list, you find the smallest thing of what's remaining, and you switch it with where you are, and then you move forward. So that you don't have to ever look at that element again. You know it was the smallest. Bubble sort looks at 2 adjacent pairs of elements and switches them if they're out of order. Insertion sort looks back over everything that was previously sorted and shifts things out of the way to put a new element in the correct position. So insertion sort is the look back. And merge sort basically is sort of the pass the buck algorithm, where instead of sorting one huge array, you say, well, I'll just sort these 2 smaller arrays first, and then I'll combine them together. And when you get to those 2 small arrays, you say, well, I'll just sort each of these 2 smaller arrays until you get down to a single element array, which is trivially sortable. There's only one thing in it. And then you just start to combine them back together in a particular way, where you look for the smallest element of each of these 2 arrays, and that becomes the first element of your new one, and so on. And we were able to talk about these algorithms using a language that we call Big O. It's a vocabulary that we have to describe the running time of different algorithms. And in CS50, when we say Big O, we're usually talking about the upper bound on runtime, or sometimes colloquially we say, what is the worst case scenario for our program? And sometimes we will use the term omega to describe the lower bound on runtime. If everything goes exactly as I want it to go, how quickly can my program run? And all of these algorithms have different upper bounds and lower bounds. The search algorithms, the lower bounds are 1 because you might get lucky. In linear search, it might be the first element of our huge array. We got lucky. In the worst case scenario, it's the very last element, or it's not there at all. But I can't know if it's not there at all until I've looked over every single one. Binary search, because it's discarding half of the array at a time, I can do it in log n. I don't have to look at all n elements to figure it out. Selection sort, bubble sort, insertion sort, all three of those, and the upper bound on their runtime is n squared. So if I have a 10 element array, it might take me 100 steps to sort those, that array. But in bubble sort and insertion sort, the best case scenario is it takes me 10 steps, where if I'm stepping through and I'm figuring out, wait, I'm not actually swapping any pairs at all. That must mean that every pair is in order, and if every pair is in order, then the whole thing is in order. Selection sort does not have that advantage because regardless, we have to look through every single element to find the smallest one. If we started to keep track of the first element, or the smallest element, and the second smallest element, and the third smallest element, we're basically just taking all of selection sort steps and just combining, we're taking 10 parallel things happening at the same time. So we can't do any better than n squared. But merge sort we can do quite a bit better. N log n in the real world, especially as n gets larger, makes a huge difference. But it comes with a trade-off too, which is that it takes up much more space. You can't sort the array so-called destructively or in place. You need to have at least two chunks of memory large enough to hold your entire array, and you're basically passing information back and forth as you go through this process of split and merge back together. Log base 2, yeah, mathematically they all reduce, but we're talking about log base 2 here, yes.
Because if you remember back to math, I can't remember what the formula is. To change between log bases, it's what, just like log of whatever new base you want divided by log of the old base, and that's just a constant.
Yeah, it's just multiplying by a constant factor, but it is log to the base 2 when we're talking about it typically in CS. Is that a question? No. Then we talked about recursion, and recursion came up because merge sort relies quite heavily on recursion in order to work. It's possible to write merge sort without it, but it's so much easier to perhaps write it with it. Recursion is a problem-solving technique where we know the solution to a very simple problem, and that's the only question we actually want to answer, is the really simple problem. Every other problem we see that's of the same spirit, but is not the super simple problem, we're going to try and drive the answer towards that simple problem by taking just a tiny little piece. We're going to solve a tiny little piece of the problem and then pass the buck. We're going to say, you solve the rest of this. Series summation, so adding all the numbers from 1 through 10. This is a process that can lend itself to recursion. We'll see some code for this in just a second. Factorial, exponentiation, Fibonacci, anything that relies on previous calculations to do the next one. All of those are good candidates for using a recursive algorithm. Every recursive algorithm has two parts. The base case, which is that really simple, this is the problem I will solve, and the recursive case, which makes the problem a tiny bit smaller and says solve this tiny bit smaller problem. And hopefully as you make the problem smaller, you get closer and closer and closer to that base case, that thing you definitely know the answer to. And then you can rely on that to bubble up and solve all of the problems that have sort of been created along the way. So here is a side-by-side of a recursive implementation of factorial. So quick definition, the factorial of a number is all of the integers less than or equal to it multiplied together, all the positive integers less than or equal to it multiplied together. So the factorial of 5 is 5 times 4 times 3 times 2 times 1. On the right is the iterative version. I'm just doing a little bit of a clever trick there with the n minus minus there to make this not look quite so big as code. But basically what this is doing is it's multiplying 5. So if n is 5 here, it's saying product is 1, product gets multiplied by 5, and then 4, and then 3, and then 2, and then 1. That's what's happening in the loop. On the left, I have a recursive implementation where I'm saying, if n is less than or equal to 0, then I'll just return 1, because the factorial of any number less than 0 is just 1. Otherwise, I'm going to return this number times the factorial of some smaller number. So I'm not going to answer the entire problem. I'm going to say, well, I know factorial of 5. It's 5 times the factorial of 4. So I'll let somebody else, I'll let another function call deal with figuring out what factorial of 4 is, and I'll just wait here with my 5 until that function has finished doing what it's doing. And eventually you'll get closer in 4, 3, 2, 1. Eventually you'll hit your base case of 0, and then once you hit your base case of 0 and you return 1, all of those other answers that have sort of been waiting on some smaller answer down the road can start to bubble back up, and eventually you'll get the factorial of 5 in both cases. These will return the same value. You don't have to do anything recursively. You can generally translate anything to an iterative approach. But it is useful to know what recursion is and how to solve a problem using recursion in case you see something like that on the test. Okay, that's it for week 3. So let's move on to week 4, where we built upon the concept of recursion by talking about the call stack. And I know that some of these slides are getting a little bit wordier now, and the reason they're a little bit wordier is because these are a little fresher in your mind, or these are rather topics that we've talked about more recently, and you have not perhaps internalized all these concepts quite as much as you've internalized like what a loop is. So when we try to do something like a swap, if we try and make a swap in another function, so main calls a swapping function, the swapping function apparently switches 2 values, but they don't get swapped in main. One of the reasons for that is that we have this thing called the call stack. Every function gets its own slice of memory, and when we pass variables to a function, we're not actually passing variables to a function, we're passing contents, or the copies rather, of whatever the content of that variable, those variables are at the moment we make the call. So I'm not passing, so if main has x and y, and I try and swap x and y, I'm not actually getting the exact spaces in memory where main's x and main's y live. It's creating copies of x and y in the swap function. It's swapping those copies, but nothing happens to my variables in main. And the reason for that is that the call stack. Each one of those functions has their own space to do their own work, and they don't share information back and forth by default in C. So every function call creates a stack frame, space in memory for all the variables it needs to do its work. And the most recently called function is the one that's on top. So when we think about a stack frame, when we talk about the call stack, really think about it like a stack of trays in your dining hall. You keep layering things on. It's only the one on top that can ever be the one that's taken if you're in the dining hall. And it's also in the case of C, it's only the case of computers, computer programming generally, it's only ever the case that the function that is on top of the call stack is the only one that's running. They're not all running at the same time. The other ones are sort of like on pause, waiting for the function frames that have been built up over it on the stack to finish doing their work before the values that are calculated in those functions can be used in functions lower in the frame, lower in the stack. Excuse me. But we can get around this problem of having information stored in one function, but we want to use it in another one by talking about pointers. So pointers allow us to access memory in other functions, and the way we can do that is by figuring out exactly where in memory that variable lives. So instead of saying, I want to know what value is in that variable, please give me a copy of it, that's how functions have, up until we talk about pointers, passed information back and forth, we're asking a slightly different question. We're asking, where in memory does this live? Because that's not going to change. And if I know exactly where in memory that variable is going to live, and I can figure that out using the ampersand operator, then I can ask a different question. Then I can instead go to that address, and whatever I find there, I can change that. And because I went to actually where that variable lived and changed it, that change will actually take effect in another function. That's quite a power that we did not previously have, and it allows us to do pretty cool things, which we talked about in week 5, like building more complex data structures and tying memory locations to other locations by having them point to different places. But pointers, remember, are just addresses. That is what a pointer is at its core. And we use those addresses to go to that location in memory and change what we actually find there. That's ultimately at the core of what pointers are all about. So if I try and change x like this will work. So what's happening in these 4 lines is I'm saying I'm creating myself a container called x, it's an integer, I'm putting the value 4 in it. Then I'm creating a pointer to an integer, that's what int star px does there. I'm creating a pointer to an integer and I'm saying its value should be the address of x. So px knows exactly where in memory x lives now. If I then say star px equals 5, what is happening there is I am going to that address. I know where x lives. That's the piece of information that's stored in px. But star px basically means go there, go to whatever address you know of, and change what you find there to be 5. So this is not saying x's address is now 5. It is saying go to where x lives and change whatever you find there to be 5 instead of 4, which is what it was before. And then if I print out x, it's going to print out 5 because I actually went and changed where x lives in memory so that the next time main references x or makes use of x, it's going to see that there's a 5 there now and not a 4. Yes? If I passed in a star before which one? I followed you up until that point where you said, yeah. So are you asking the question, what would have happened if we had passed in before and after instead of ampersand before and ampersand after? If you pass in star before,
So,
this is probably best done with a diagram.
Yeah.
yeah. So I don't remember the exact type of before and after. Let's just say int before and after. So
It's a structure.
yeah, but it's like struct.
R usage.
Is that what it
Yeah,
is?
doesn't matter.
So int before and after. So if and get our usage is the function, right? Oh, so it's struct our usage and then get our usage. Okay. So the function we end up passing it to, get our usage, something like this. So we need to pass it as and before, since if we just pass before, without even knowing what get our usage is, if we just pass before, we know that this can't possibly change the actual value in before because it doesn't have any way of accessing this memory. So get our usage will have a copy of, if you look at the call stack. So let's say this is in main, and we have somewhere in here space for before and after. So when we call get our usage, like this will have its own copy, some memory in here for the value of before. Whatever get our usage does with that will only change this place in memory. But if we instead pass ampersand before, now get our usage can actually change this value because no longer does it have this, it instead has a pointer to b. And by having a pointer to before, it can now follow that pointer and change this value. So after get our usage, before can be changed. Now you were asking what happens if we were to pass this. This doesn't make sense. So this would be saying we want to follow the pointer before, but before is not a pointer. So whenever we see a star, that basically, if we have some variable that is an integer, then ampersand x is going to give us an int star. So we could say int star px equals ampersand x. And ampersand px is going to add another star. So we get a pointer to the pointer to x would be just taking another ampersand. So ampersand is just going to keep adding stars while using the star takes away stars from the type. So
Pointers
now
are
I can
very annoying because they use star in multiple ways.
yeah. So if C were nice, they wouldn't have used star both here and in this context. So don't confuse those two types of stars. But I can say int star px2 equals star ppx. And this is a valid expression since ppx is an int star star. I am dereferencing it once, so I'm going from an int star star to an int star, and that's a type of int star px2. And now I can say int x2 equals star px2. Or I could say int x3 equals star star ppx, because ppx is an int star star, so dereferencing it twice gets me just an integer. But I cannot do anything that involves star x3 because x3 is not a pointer type. So trying to dereference that is not valid.
Scary, right?
Basically,
Stars and ampersands cancel each other out.
yeah.
Effectively.
So you can say in C, I guess not starting with a star, because star x3 is still invalid. But I can say in C, ampersand star, ampersand star, ampersand star, x3, and all of these will just cancel each other out, and this is ultimately just saying x3.
So to boil all of this down back to the question that was asked before, you can only dereference or star something if something is an address. And here, before and after are not addresses, they are integers. If they were int stars, I could do it, because then they would be pointers to integers, or the addresses of integers. So you can only take the star of something if it is an address. Excuse me, yes, you can only take the star of something if something is address, or you can only dereference something if that something is an address.
Yeah, every time you dereference something, you get back a data type that has one less star. So you can think of it that way, and because int before and after they weren't pointers to begin with, we didn't declare them as int stars, it wouldn't make sense to dereference them.
Yeah, so no matter what type of pointer problem we throw at you, if you do not understand it, you can always just go back to like manually drawing boxes and arrows and stuff, and if you just follow step by step, you have to end up at the right answer. So without even understanding if we throw something with like an int star 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 at you, you could still just follow arrows and follow dereferences and follow ampersands, and things will work out.
Yeah.
So that got to Rob's first example here, which is that if we just passed in not ampersand, if we just passed in before and after, we would have effectively created copies of before and after, changed those copies, and our original ones would have remained unchanged in main, so that if we printed out before and after, it would print out main's version of before and after and not get our usage's version of before and after. So we had to send in the addresses of those things so that get our usage, which is a separate function, could change what it sees there. Oh, you're right, it was calculate.
So the advantage to that is, again, whenever we pass something to a function, we make a copy of it. So imagine whatever this struct actually was supposed to be, struct get our usage.
They're very large, those structures.
Yeah, or struct our usage. So imagine that this structure has 1,000 fields. So if we just passed before to a function, that means over here, we're going to be copying 1,000 fields into the function that we're calling, into the stack frame of the function that we're calling. Whereas if we just pass a pointer to it, we pass a single pointer, 8 bytes, that references those 1,000 fields.
So that becomes a question of efficiency more than that. But yeah, sorry, I was not following where you're going with the question. But yeah, that's why we do it, is because it's going to save us so much time just copying this thing, which we could do, it would work out just fine, but perhaps not the most efficient way to handle.
Additionally,
like
the function that we were passing and before, like ampersand before into, would probably not be able to take in just an int because of the way we've declared it.
So to sort of rehash this idea, this would not work. If I printed out whatever this program prints out, it's not going to be 5, it's going to be 4, because in this case, change has its own copy of x. It can't do anything with it. Or it can change its own thing, but we're not printing out what change is doing. We're printing out main's x. But this would work just fine. So notice that I've now changed my prototype for change to accept a pointer, and I've changed what I passed to change to be the address of x and not x itself. And so in this case, this function, or this program would print 5. So the first one printed 5, the second one printed 4, this one printed 4, this one prints 5. So then this is the point where we finally revealed that strings really are just pointers at the end of the day. The variable name of a string is really a pointer to the first element, or the first character of that string. And that's why we can say something like this: string s equals cs50, string t equals cs50. And if we say something like if s equals t, so remember we use two equal signs to check for equality, we will get false. It will not be true. And the reason for that is that s is one address of memory, t is a different address. Even though ultimately the content of those strings is exactly the same, they live in two different points of memory. And so when I say is s equal to t, it's basically asking is the address where s lives equal to the address where t lives. And they're not the same address. They're two separate variables, two separate containers, and that's why that doesn't match. We have to use strcomp, remember, when we're comparing two strings to make sure that they have the same content, so it does something slightly different. And the other cool use for, oh, sorry.
Why is that the case though? Like, 'cause if they're stars, right, then somebody would go and look at that memory, right, and it wouldn't be value. So why wouldn't we have X?
Good question. So when I say something like this, I'm not dereferencing anything. I'm saying string s equals cs50. So what's happening is I'm getting a chunk of memory. So I say string s equals cs50. I basically get something like this, and I get something like this. CS50 \0. And that does that, but I'm not actually dereferencing it. It's still a pointer just to its first element. And the way that the system knows to print is it just goes there and it just reads what it sees, which is not quite, we're not actually dereferencing when we're making an assignment like this. If I then do the same thing, if I say s equals t, if I did something like that, that would work. They would point to the same thing. But if I say separately t is also cs50, it's not going to just send me to what already exists. It's going to do exactly the same thing that it did before. But these two variables, just like any two variables, live in different points of memory. If I had said int x equals 5, int y equals 5, if x equals y, that works, but that's because int is not an address, it's just a container.
So remember when we draw these arrows, like the computer isn't actually storing arrows in these boxes, they're storing addresses. So if this happens to be at address 0x10 and this is at address 0x20, then when we say s equals t, what it's checking is does 0x10 equal 0x20, which it doesn't.
Because really what's happening is there's not actually arrows in there. This is just its own box that says 0x10. Just like if it was an integer, it might be 5 or 6 or something like that.
We just represent this visually as, yes.
Because it's more helpful to see it that way, I think.
So if we were to compare both, we wouldn't be comparing their values, but where they are in memory.
Good question, though. It is a tricky, pointers are definitely probably the trickiest topic that we talk about, I think, in the course generally. So when we are running programs and we need memory while our program is running, we might not have anticipated needing so much space, we can use a function called malloc to dynamically allocate memory or give us memory while our program is running. Malloc just asks you to pass in a parameter where that parameter is how many bytes of memory you need. And so since you don't necessarily want to memorize how many bytes of everything is, you can use this thing called sizeof and say I want to malloc size of int. And it will give you however many bytes an integer takes up on that system. And if you're using a really old computer, it could be 2. But you will get back exactly as much space as you have specifically asked for. The trick, though, is that you need to free all of that memory. So when we talked earlier, we had this picture that Rob was building of the stack frame. There's another chunk, there's another area of memory that all ends up being the same thing, but the lower portion, as we usually describe it, is the stack. And the upper portion we call the heap. And when we dynamically allocate memory, it comes from the heap. And unlike stack frames, which once you finish a function, that stack frame is destroyed and all of the memory that it was used is automatically given back to the system, memory in the heap is not. It just kind of stays there just until you explicitly say, I'm done working with it, or you free it. Which could mean that if you fail to free memory, this heap starts to get bigger and bigger and bigger, and because the heap and the stack really are just one big thing, growing from different directions, you can eventually sort of crash into it, and that would be a big problem. That can be a cause of a segmentation fault. Or if you fail to free your memory, you can have something called a memory leak. And if you've used particularly some older forms of web browsers, some of them are notorious for leaking memory. They allocate memory for themselves, and then they finish working with it and they don't do anything. And if you leave your web browser open for like 5 days or something, you can find that your computer is running really, really slow. And the reason for that is that this one program is hogging up all of the memory that your computer has. You have a finite amount, like 4 gigs or 8 gigs maybe of RAM. And it turns out that your browser is just stealing all of it and not doing anything with any of it. It just hasn't released it back to the system. And we have a tool called Valgrind that we use to detect these kinds of memory leaks in our own programs. It tells us how many bytes we have left unfreed that we still have allocated. It'll also give you clues about when you do something with memory you're not supposed to do, but apparently you can get away with. So like Rob said, if we have this string that is of size 5 and we access the character number 5, we get backslash 0. If we access character number 6, we're probably going to get lucky most of the time. We're probably not going to suffer a seg fault. In that case, we can, but we probably won't. But it's called an invalid read. We've gone beyond the memory that we have explicitly been told that we have. And so Valgrind will actually tell you when you do things like this. And so that's why in problem set 5 we have you use Valgrind to make sure that your program is memory leak free and also that you're not doing anything invalid or illegal with memory that you shouldn't be doing. Among those things that you can do if you overstep the bounds of your array is a different kind of overflow than we talked about earlier, and this is called buffer overflow. If I have a string and I've said this string is going to be no more than 12 characters, the system is sort of relying on me being honest about that. It's going to give me 12 bytes and it's going to say, okay, well this next function that's going to get called next is going to use the bytes just beyond those 12 because it's the next thing up in the stack. So if I then read a string and store it that's 16 characters or 20 characters and I store it in that string, I'm now sort of encroaching or overriding memory that belongs to another function. And that can result in a buffer overflow. And we can do really malicious things with buffer overflow attacks. We can try and write the address of a totally different segment of memory where we have written some virus and hope that we end up doing something where when that function returns, it doesn't return to where it should, it returns to that memory address that we just wrote. That's the kind of thing that you can actually do with a buffer overflow attack, and then suddenly you've executed this virus on your system. Fortunately, that will not happen in your IDE, but it is the kind of thing that actually can happen if you don't defend against malicious users, overwriting the bounds of your array, which you can do by checking the length of the string before you store it that you just read or something like that. Any sort of defensive tactic that you can employ to prevent something like this is a good thing to have in your code.
4 minutes.
We have 4 minutes. That's okay, we're almost done with week 4, and week 5 is not too long either. At the end of week 4, we talked about structures, which allow us to encapsulate data. So we can have this notion of a student who has many different attributes. So we can have this, we define a structure as struct student, and then in here we have 4 fields or members of our structure. And we can access those fields, we can treat them as variables once we have declared a structure or declared a variable of this structure type. We can then access the fields of it just like we could with any other variable. So we can create a struct student Maria, and we can copy the name Maria into maria.name, which is accessing the name field of the Maria variable, which is of data type struct student. We can copy Cabot into our house. We can say maria.year equals 2018, and we can say maria.gpa equals 4.00. Just like we could do with any other integer, we can assign it to a value. We could assign a float to any other thing of data type float, and we can copy strings into that location. But we can't say is maria.name equals Maria, because then we're having that same problem we talked about earlier with strings and addresses. We're not going to quite do exactly what we are intending to do in that case. So that's structures. And I'm going to quickly just go through week 5, and if there are any questions, we can stick around after, but I do want to cover these last couple of topics. So in week 5, we introduced linked lists. So arrays have this problem where they are of a fixed size. You say at the beginning of your program, I need an array of 30 integers, or I need an array of 20 floats, or whatever. You can't really vary that, though. If you decide you need 31 integers and you only allocated 30, well, you're kind of out of luck. You're going to have to give yourself a new array. But linked lists are much more flexible. They allow us to grow and shrink as our data set grows and shrinks. And so it's great for something like problem set 5, where we have this dictionary, and yeah, we happen to know that the dictionary that we provided you was 143,000 some words, but maybe you get a different dictionary. You don't know how much space you're going to need ahead of time. What you can do is instead build this linked list where every element is a node, which is what we usually call it. It's a structure, basically. And each one of these nodes has usually at least 2 pieces, the first of which is data, what we're actually going to store. If it was an array, it's what we would store in the array location. But it's not, it's a list, so it's whatever we would have otherwise stored if it was an array. But then we have this additional thing of a pointer to another structure of the same type. And basically what this allows us to do is to sort of create this chain where we have this, it's a linked list, really. And up here, we have, we store, maybe we're storing words, we store cat here, and then cat is chained to dog, and that's chained into bird, and then maybe there's nothing else after bird, right? That's the end of our linked list. So this last element points to null. But we could grow this list as large as we wanted to. If more data kept coming in, we could just give ourselves space for a new node. And maybe we want to store fish. That is a really bad rectangle. It's coming in from a weird angle. And then I could just say, well, instead of this pointing to null, it's not the end of my list anymore. Apparently I'm emphatically insisting it's null. Instead of pointing to null, it's going to point here. And then this is the new end of the list. That's null. And so we can just kind of grow this list. And similarly, could we shrink this list? We could pull elements out if we needed to, or if we wanted to, just by deleting it and rearranging those pointers again.
0 minutes.
I have 0 minutes now? I still have 2 minutes on my clock. Insertion and deletion are constant time. You can insert at the beginning of the list pretty easily. Lookup and search, though, is O of n. You have to go, you have to chain your way from beginning to end. Stacks and queues are just sort of modifications on a linked list. A stack, the rule with a stack is that you can only ever insert at the front of the list, and you can only ever remove from the front of the list. A queue, you can only ever insert at the front of the list, and you can only ever remove from the back of the list. And there are a couple of array-based implementations for this that are also available, and they appear in the lecture source code. Trees, so week 5 is all about data structure. So trees are a type of data structure that usually has 3 parts to it. Data and 2 children nodes, 2 nodes that live below it, and maybe nodes that live below that, or so on and so on. And it's just another way to build this hierarchy of information. There are binary trees where every child of a node, there are no more than 2 children for any node. Binary search trees where that's also true, but the tree is sorted so that everything to the left of any given point in the tree is less than it. Anything to the right is greater, so you can use binary search on it. Tries have an arbitrary amount of children, so that would be very useful for problem set 5, because you could have 27 children or however many you wanted to. Lookup and search are better, but not perfect in trees, but insertion and deletion are still constant time. And then we had hash tables, which are a combination of a linked list and an array. So instead of having 1 linked list, we have n linked lists, and we have this hash function that will generate for us a number between 0 and n. And all we have to do is take the data, run it through our hash function, get that number out, and then store the data in some node at linked list, whatever number was spit out by our hash function. So if it spit out 6, we go to array location 6, and we add that node to linked list number 6. All right, so that's going to wrap up the test review. Those were all the topics that we've talked about in the course. If you have any questions, Maria and Rob and I will stick around up front. Otherwise, good luck. The test will be released Friday afternoon, and office hours tonight and tomorrow.
Thanks, guys.